Hello, this is Mahan Didia. This is the fourth module in the book on liquid formulation utilizing qubits video format. The focus of this module is on physicochemical characterizations of emulsion. This module contains two related videos, sub-modules. One on immiscible liquids and emulsifier, and second is on classification and types of emulsions. As described in earlier module, emulsion is a biphasic dispersion. The dispersed phase is composed of small globules of liquid that's distributed throughout the continuous phase in which the dispersed phase is immiscible. That is, there are two immiscible liquids. So let's define what is miscibility and what is immiscibility. Miscibility means substances mix in all proportion forming homogeneous solution. Because of that, miscible liquids are harder to separate as they dissolve in each other. And miscible liquids are often separated using distillation if the boiling points are sufficiently different. Immiscible liquids do not mix with each other in any substantial proportion. Well-known example is oil and water. It is possible to shake the liquids and get them to mix temporarily, but they will soon separate. Separating immiscible liquids is simple to achieve because they are not soluble in each other. Here's an example of miscible and immiscible liquid. Alcohol and water are miscible and form homogeneous solution in any proportion, as shown here. 20 milliliter of water is colored red so one can see it, and it's mixed with 80 ml of alcohol in first picture. In second picture, 50 ml of each are mixed, and in third picture, ratio is 80 milliliter of water and 20 milliliter of alcohol. And if we were to mix them, we will get a homogeneous solution as shown here in the last picture. This we can compare to water and oil. We take 50 milliliter of water and 50 milliliter of oil and mix it. Mixture will separate and will form non-homogeneous mixture. Water and oil are immiscible and form non-homogeneous mixture in any proportion. Let's look at actual formation of the globule of oil upon mixing, and then very fast separation of oil from water once the mixing is stopped. We can see that in this video. In this case, olive oil is mixed with water, and you can see the globule of olive oil forming. And if we mix it, we can see it forming a globular. However, oil molecules, as shown here, are not attracted towards water molecule. An oil molecule will attract towards other oil molecule. Similarly, water, which will form very strong hydrogen bond with another water molecule, they will start separating. And oil in this case has a less density, so it will float on top. We can look at that at a molecular interaction level. Compare immiscible to miscible. In this case, oil is methane molecule as shown here, and solvent is water. And the charges are shown here. If there is a positive charge such as hydrogen, it's +1 and shown as yellow. And oxygen, which has a negative charge, shown in purple. Methane does not have substantial charge on it. It's nonpolar. It's shown as white. Immiscible droplets separate because force of attraction between the molecules of same liquid, molecules of either methane or water, attraction within the molecule is much greater than the force of attraction between two different liquids, such as water and methane. We will see that separation in this video. Solvent is water, and oil is illustrated with methane. And we can see electron density, negative charge, and hydrogen having a positive charge. And methane here is nonpolar. Solute-solute dispersion, London dispersion forces are weak. Solute-solvent, London dispersion forces are weak. Very strong is dipole-dipole hydrogen-oxygen interaction. So as we mix it, water molecule will start collecting and will separate methane or oil, squeeze that out. That in compared to miscible liquids, where force of attraction between the molecule of same liquid, water, and in this case shown as plus and minus a polar molecule, is less than the force of attraction between water and the negative charge, water and the positive charge. Polar molecules will dissolve in polar solvent. Similarly, non-polar molecule will dissolve or they will be miscible in non-polar systems. Emulsion is a dispersion of one immiscible liquid with another immiscible liquid. Example would be, we can put an oil in water, it will form globule and it would separate. Disperse phase, that disperse in the shape of globule, is known as internal phase or disperse phase. The continuous phase is called external phase or a continuous phase. In order to stabilize these globules, we need to provide emulsifier to prevent the phase separation. So emulsification itself requires two steps. Number one, energy to disperse liquid to create an emulsion globule, and second, prevent coalescence of globule and separation of that phase. This is accomplished by emulsifier. Emulsifier can be looked at as a mediator compound that keeps immiscible liquids together. Emulsifying ingredients are also called surfactant. The emulsifying ingredients molecular structure includes hydrophilic and lipophilic ends that attracts aqueous and oil phases. We need to provide an energy during the emulsification. Relatively large amount of energy is required to form an emulsion after the chemical conditions are correct. Emulsifier is properly selected. Generally, mechanical mixing is commonly used that breaks apart the dispersed phase and it evenly distributes that throughout the continuous phase. It depends on agitation factors, rate of addition of dispersed media, temperature. Emulsifiers are also known as surfactant. Emulsifier molecule has two parts: hydrophilic, that is water loving or water soluble portion, and lipophilic, oil soluble portion. Lipophilic end, shown here in gray, attaches to oil portion of. Hydrophilic end, shown here, is water attracting layer around each globule, and that's how it separates globules. Emulsifiers then prevent droplets from agglomerating. Three most common types of emulsifiers are anionic. This is an anionic group. Cationic. Cationic group here shown is attached to the lipophilic end. And non-ionic. The head does not have any ionic charge. The tail or lipophilic end does not have any charge. So emulsifiers have two parts. Let's look at emulsifier in a little bit more detail. Emulsifiers have two: hydrophilic, that likes water, and hydrophobic or lipophilic, that dislikes water. So when we form a emulsion, oil is suspended in water, is shown here, and water, on the other hand, is suspended in oil. Common examples are mayonnaise, creams, milk, and common example of water and oil are butter, margarine, and other products. Emulsifier anchor hydrophilic part into water and its lipophilic part into oil. Its orientation, concentrations of water and the oil portion will determine whether it is a oil and water emulsion or water and oil emulsion. This video, emulsion formation of oil and water with an emulsifier. So oil is added into the water phase. It will not form an emulsion. If you provide mechanical energy, it will provide globules, but it will break because water is a polar molecule, and polar molecules will attract each other through a hydrogen bond. If we add emulsifier, it will still not make an emulsion until we mix it. We provide mechanical energy, conditions are correct now, and once we mix it, it will form an emulsion. And in this case, oil droplets, an emulsifier with a polar head and non-polar tail. It will orient in such a way that non-polar tail will get absorbed into the oil and the polar portion will remain exposed to water. Emulsifier by itself will not form an emulsion if its hydrophobic portion and its lipophilic portions are not balanced properly. Many compounds are composed of hydrophilic and lipophilic that can be used as an emulsifier. It depends on the vehicle, continuous phase, and the oil phase. If the hydrophilicity, the water-loving portion of the molecule, is greater than its lipophilicity, molecule will disperse in water as shown. One with a greater lipophilicity than its hydrophilicity, depending on the vehicle, will disperse into oil. When hydrophilicity and lipophilicities are well balanced and it meets the required physicochemical characterization, it will form stable emulsion. So the interface of two immiscible liquid, in this case water and oil, and the orientation of emulsifier to form a stable emulsion.